let me start. I'm Siavash from part of network optimization and machine learning teams in WSP New Zealand. We are based in Auckland. I have a PhD in transportation engineering from University of Auckland, work on post-disaster road network resilience assessment. I joined WSP last year in April. We are as a team of network optimization and machine learning involving in different projects related to data, which includes data analysis, machine learning, image processing, algorithm development, data visualization, post-impact evaluation, traffic modeling, and also resilience. Today on this webinar, wanted to share our experience and the new method that we developed to assess trip resilience following major incident or disasters. Yep. So first, a little bit introduction on the network, on the resilience, and then I will discuss the trip resilience, the new method that we developed. And there is two case studies, one for Auckland Harbour Bridge after the incident that happened, and the another one is for Alpine Fault magnitude 8 earthquake. And at the end, there would be the QA session. So what is the resilience? Most of you most probably work with the resilience and know that what it is resilience. This is the typical resilience concept that it is usually used when we talk about resilience. This is showing that the performance of the network is as business as usual. If any hazards happen, you can see that there would be a drop on the performance of the network, which it is completely related to the robustness of the network. And if we do any hazard mitigation, as you can see here, so the robustness would be increased and then the drop would be less, which caused the increase in the resilience of the network. And then depending on the rapidity, resourcefulness, and redundancy, we try to get back during the recovery time, we're trying to get back to the normal condition. And the shape of the recovery depending on these three components. This area showing the resilience of the network, and you can see that with risk mitigation measures we can increase the resilience. This is the typical resilience concept which we usually use for the assets. The question at that time was that how we can try to get to assess the performance, the resilience of trips, I mean users of the network, based on these components: robustness, rapidity, redundancy, and resourcefulness. So we come up with some ideas that how we can assess the resilience of trips. This is conceptually showing that how we measure the trip resilience on the network. It is the same as the one that I showed you. So during the recovery period, we are trying to get back to the normal condition. So if any disaster happen, the first thing is that whether travelers can start their trips or not. So assuming that the travelers cannot start their trips, let's say 60%, so we will have the first drop on the performance of the network because of eliminated trips. I mean, these are people who cannot start their trips because the road blocked, or even they postpone their trips because there is a congestion on the network, or even change their mode. So we assume them as the eliminated trips, and these, let's say 40% are robust trips that they can start their trips. So this is the first drop on the performance of the network, but these 40% also important, and we wanted to check that they will go with the same experience, I mean the business as usual travel time, or not. So the second drop would happen when they will face some extra travel time when they start their trips, and this is because of the redundancy. And then we call it as the redundancy impact. So two drop will happen, one for the trips and the another one for the redundancy. And the combination of these two can give us the trip reliability on the network, which is measured at each time. So at T0, you can see that the trip reliability based on these two, it is about 20%. And during the time when we go to the recovery, we will reach to T1. And as you can see, these dashed lines showing the trip robustness. So more trips start to happen. and we have this amount of trip redundancy, and the trip reliability increased to this month around 60%. And then we will go for the T2 during the recovery, and again we can measure trip reliability at this time. As you can see that T2 we just have some eliminated trips, and all of the trips can go with the business as usual in travel time, so we don't have any redundancy impact here. And just some eliminated trips at T3, you can see that it is they get back to the normal condition. So this is the curve of the trip reliability, I mean this gray one, and then this area over under the curve of trip reliability showing you the trip resilience. So the novelty of this method is that we combine all of the components of resilience, I mean robustness, redundancy, and recovery in just one measure that you can see here. But how we can apply this method to case studies? So here the first study is about Auckland Harbour Bridge. New Zealand has two main islands, one is known as South Island and the another one North Island. The first case study is in the north, here Auckland, and the second one is in the South Island, which I will go through that. So it is Auckland, and if we look closer, you can see that this is CBD, and here is Auckland Harbour Bridge, which so this is State Highway 1 connecting north to the south, I mean north of North Island to the south of South Island, and this is State Highway 18 and 16. Normal days, the Auckland Harbour Bridge is connected from State Highway 1 and connecting north to the south, short route. But if anything happened on Auckland Harbour Bridge, the alternative route would be from State Highway 16 and 18, which is known as Western Ring route. So what happened on the network on that day? It was around a year ago, 18 September 2020, that there was a storm on Auckland, and when the truck was driving on the bridge, so the wind blew over the truck on the structure of the bridge, and as you can see the struts damaged, and then they needed time to go through that and change and fix the structure and then make sure that everything is fine. It took around 2 weeks. The other thing about Auckland Harbour Bridge is that it has 4 lanes at each direction, and we have barrier in the middle, you can see, and then we can change the configuration of the network, the layout. So in the AM peak, southbound it is 5 lane and northbound it is 3 lane, and in the PM peak, vice versa. Northbound it has 5 lanes and southbound has 3 lanes. We are, as a team, part of the Auckland System Management Alliance, ASM, and we are part of the journey optimization team. At that day that the incident happened, we asked to provide daily network performance on both directions. I mean the State Highway 1 southbound and Western Ring route that connecting the north to the CBD. And we had access to the TomTom data. We have access to TomTom data, so we have travel time and speed on the network for hourly base. And then we also have the traffic count data on the network. So the traffic count data also we get from the data. The TomTom also was quite unique opportunity for us to get the speed and travel time on the network. And we monitored, as I will show you, for each day, created the heat maps and monitored the network performance of the network. After the incident, there was a request from the client that how we can use the new KPI to assess the performance of the network. And at that time, we tried to use this trip resilience to measure the resilience and reliability of the network for at each time. These are the heat maps that we created at each day. If I want to go through for one of them, it is the timeline, showing the timeline from midnight to midnight based on hourly base. And these are the main interchange on the network between Onewa and Shelley Beach Road. Here is Auckland Harbour Bridge. And you can see that in the AM peak, there is a little bit congestion for the AM peak, which it is fine because we face some congestion on the network. You can see that the speed drops, so it is congestion here, but the rest and the PM peak, there is no congestion. And the day that it happened, so you can see after 11 that the incident happened, there is a big congestion over here until I think after the PM, 8 p.m. And the next Monday, you can see that it starts from early morning until around 8 p.m. and also for the next day, Tuesday. And depending on the condition and layout of the network, there was congestion on the network that we use to measure the trip reliability and trip resilience. These heat maps showing on the Western Ring route, on the alternative route. So you can see on the next Monday, there is a congestion in the AM peak, so showing that people also start to use these alternative routes for traveling. And there are some congestion for some days. That means people start to use more these shortest route. And then based on the travel time that we get from the TomTom and also traffic count data, as I mentioned, so we start to measure the trip reliability and trip resilience. Here I'm showing you two of them, AM peak and PM peak. So you can see that this is showing the trip robustness, I mean reduced flow on the network. So you can see that how the flow reduced on these two corridors. And then these areas showing the impact of increased travel time. And then here we have the trip reliability for each day. So the AM peak is the worst because usually it is 5 lanes, but at that day it was during the recovery period it was 2 lanes or at last 3 lanes. But the PM peak it was fine because except some days and the first, the next of the days you can see that there is no redundancy impact, and they went to the network with the same travel time as business as usual. So at this case study, we used it was the real incident. So we see that how we can apply this method for the real incident on the network, and we use also real data, I mean travel time and volume, which was opportunity for us. And also we checked that how the impact of reduction lane to 2 or 3 lanes on the Auckland Harbour Bridge, how it would be the trip reliability. But the second one, it is for the Alpine Fault, which it is on the South Island. You can see that this is Alpine Fault, which it is around 600 kilometer extents on the South Island. It is usually on the west coast of South Island. Here we are, and it is one of the major fault system in New Zealand. There is high probability of rupture in next 50 years, which is quite high. And if it happened, there would be severe damage to lifeline, especially to the road networks. So the model developed in Aimson for the whole South Island. We calibrated the network and also validate the network for a disaster, because the Kaikoura earthquake happened, and then we had the opportunity to validate the network for an emergency condition. And these figures showing the business as usual condition on the network. So you can see this is again State Highway 1 connecting north to the south, and it is the main corridor on the South Island. The another one is State Highway 16 on the west coast, also connecting north to the south. There are 3 connection between there is 3 connector that connecting east to the west. So State Highway 73, State Highway 7, and also State Highway 63 and 6 that connecting east to the west. And if anything happen on Alpine Fault rupture, so these are 3 main: Westland, Grey, and Buller are the 3 main districts that would be impacted highly after a disaster. So they are here. I used for the scenarios, I used the Alistair Davies scenarios from University of Canterbury. He worked on the how the impact of Alpine Fault on the road network. So I got where the disruption happened based on his scenario. 1 day after that, 1 week, 1 month, 6 months, and beyond 6 months, which I assumed 1 year for my scenarios. And these are the outputs of the
Looks like We don't have audio with Siavash. Let's wait just a minute to see his connection. Apologies for this.
One week after disaster, and this is for after 6 months. After 6 months, State Highway 7 will be opened, and then there is connection, so more trips start to happen between the east and west. So there is less eliminated trips, and also some some roads between State Highway 65 will be open, and then the connection. And also after a year, you can see that more red roads will be open, and then we will face some more trips that can start to happen. But still on the wasteland, you can see that these areas still closed, and there is no trips from here to another part of the network. Let me, okay, yep. So this is the result for the trip resilience for this is for the whole South Island, and these are for the main districts on the network. So you can see that here for the South Island, it is just 2% drop on the network, and it is obvious because on the West Coast, it is just only 2% of total trips on the network for the whole South Island, and then it will get back to almost the normal condition. But the Grey and Buller and Westland, the three most impacted districts, you can see that how it changed. How it changed. So for the Buller, you can see that it dropped. Most of the trips would be eliminated, and then it start to get back. And then we try after a year, it will almost most of the trips can occur. On the Westland, you can see that the impact of redundancy, I mean increased travel time, it is big, and you can see that the differences between two compared to the another two districts, because as I showed you, it is on the area that if and State Highway 7 is still closed, I mean the shortest route, so they will face a the long detour that they should take to reach to their destination. So this is that what happened on the network. For the second one, yep, this we use the hypothetical data and the earthquake and what happened on the network. It was the long-term recovery that we tried to use, and we use also modeling outputs. There was no real data, so it was the modeling outputs. And a different recovery plan for this kind of incidents can be investigated. I mean that we can try to see that if we start to open State Highway 7 instead of State Highway 73, so how it would change the trip resilience on the network. And for the summary, the as I mentioned, the novelty of this method is that we're integrating all of components of resilience. I mean, robustness, redundancy, and during the recovery time. So it is the first time that we integrate all of these components in just one measure, that it is the trip resilience or trip reliability. So trip reliability at each time, and trip resilience is for the recovery time. Two case studies were investigated, one using the real data, which it was the Auckland Harbour Bridge, and the another one using the modeling data, which was on the whole South Island and using the modeling outputs. The application of this method is that we can use it to support the increase of resilience in infrastructure. I mean, we have different, as I mentioned, different recovery plan. So ordering of reopening of the route is important after disasters, and so we can check that which order is the impact of each order, and then we can compare the different options. And also we know that if we can shorten the recovery period, also it is important. So we can also check if we put more resources and more budgets, then how would be impact on the resilience of the trips. Then another thing, we can prioritize the different mitigation measure. Then we can see that if we start to mitigate, and which option is the best. And at the end, we can also work on criticality of the network. So we can check that which part of the network is more critical based on this measure. If it is, so in this case, we can use the trip reliability instead of trip resilience, because we don't have recovery time. And then based on the trip reliability, we can find out which part of the network are more critical than others. And we try also to use the same method to evaluate the resilience of the network after evacuation. These are other asset management webinar series that please feel free to go through that and join and register for any of them. They are quite interesting. Thank you so much. If there is any question, happy to answer. Thank you.
Thank you, Siavash, for your presentation. So just a reminder, you can log your questions now in the question box on the GoToWebinar platform, and also a PDF version of the presentation is available for you to download in the handout box. I will start with the first question. How this method can be applied to a small incident or even daily basis, given that the recovery period is an element of resilience?
Yep, okay, that's a good question. So as I mentioned, so in this method, we can measure also trip reliability. So if it is the incident and we have the recovery depending on the incident. So for instance, if the small incident, maybe some hours and then we can recover. Or if not, it is just big incident, that the same thing that happened on the Auckland Harbour Bridge. So depending on the recovery period, we can apply this method and see that how was the trip resilience, or even for at each period of time, we can measure the trip reliability based on the reduced flow on the network and also increased travel time. And as we have also have a plan in our team to using some machine learning techniques, and we have the live dashboard. So we are trying to add this new KPI, the trip reliability, as a new KPI for this dashboard, and showing that how the trip reliability would change on the daily basis for each section of the network based on the historical data that we have. So we can use the travel time, the historical travel time on the network. So we have the historical data. And then also we have the historical data for the traffic count data on each section of the road. So we can easily measure the trip reliability and then compare for each day that how it was the reliability of the network.
Thank you. Given that the last value is on percentage, how two critical links with the same resilient values, let's say 70%, can be prioritized? Are they the same?
Yep. Okay. So on this, yes, the final one is percentage. So maybe there is two links. If we, for instance, let's say that for two options that we have, it is just 70%. Then if we have another measure that we called it as the equivalent number of impacted trips. So we are weighting based on the flow on the network. So this percentage and also flow on the network, we can prioritize which one is the most it is the best option for us, or the most impacted one after disaster. So there is another measure that I didn't have time to cover in here. But it is the equivalent number of impacted trips that we can measure, and then based on that we can compare these two options together to see which one is the highest and which one is the lowest, and then compare these two together.
Thank you. How do you effectively integrate high-level node-to-node assessments with site-by-site mitigations? Do you use big data?
Okay, that's also a good question. So for the mitigation also, it is the kind of different option. So for each section, we wanted to do some, let's say, hazard mitigation measure, and then we want to check that what would be the impact on the trips. So again, this is the same. So we have, for instance, if we have the OD matrices or if we have the modeling data, we can use the output, or if we have the big data, for instance, as I mentioned, historical data, and also for the travel time, for the flow on the network, then we can use these sort of big data and maybe using some machine learning techniques and this sort of data analysis, and then we can measure the trip reliability, most probably trip reliability on the network, and then we can compare these different mitigation measures to see which one is the best option for us, given that which mitigation measure we use. So it is possible to compare different mitigation measures based on the big data or even the modeling data.
Thank you. The next question is, did you calculate how much travel time would be saved by using the best reopening sequence compared with the worst?
Not really. We didn't check that how much travel time would be saved, but based on the method that we have, I mean the trip reliability. So the travel time, it is just one option, but as I said, we integrate both. I mean the reduced flow and also increased travel time, these two options together. So we integrated these two in one method and one measure, that which we can call it as trip reliability at each time. So if we use this measure, we can compare how much it saved. As I mentioned, for instance, we can use the something like equivalent number of trips. So this measure can be used instead. We have this measure that how much, let's say, trips would be saved comparing these two options, or these two, the worst and the best case. So we have the kind of measure instead of the just travel time, but it is also possible to measure, to compare based on the travel time, because we already have the differences between these two.
Thank you. The additional question here to this question was also, did you calculate an economic benefit?
Yep, this is the question also in another presentation they asked me. No, we didn't have chance to use the economic evaluation for these projects. We have in our mind to, at the next phase, maybe try to use economic evaluation and measure that how was the economic cost for these two projects. But no, at the moment we didn't go through that method and measure the economic cost of these two based on the data, because the data is there, but you know, they didn't ask us and we didn't go through that.
Okay, thank you. We'll take the last question. How can drone-based surveillance supplement the subject trip resilience assessment methodology?
Okay, so the drone can be used to extract data. I mean, after disasters, or maybe, I don't know, for the condition of the network, we can use drone, as we also try to use drone on some of our projects. And then there's maybe some, I don't know, image processing, machine learning techniques we can use, and then extract data for the traffic volume, or even for the travel time, and then we can use these for as an input to this measure, and then we can assess the resilience. Even though, as I mentioned, to the TomTom, we have access to TomTom, so, and we also have the IP to use the sample size of the TomTom to get the traffic volume of the network, and then based off the traffic volume and also travel time, both of these, we can also measure the trip resilience on the network. So the data, it is important in, I think, most of the projects. So drone or other kind of techniques, it's also just the input, give us some input for the projects and for the different measures, and then we can, based on that measures, we can start to assess. And the data is so important. If it is good data, so the measure would be accurate. If not, then you know that it is not a good example. Yep.
Thank you. Thank you, Siavash. We're at the end of our webinar session, so please feel free to follow up directly with Siavash via the contact details shown on the screen. And I would like to thank all attendees for joining today. Thank you for your time. Apologies for the short technical issues, and thank you for your patience. Thank you. I will
Thank you
wrap up
so
the
much.
webinar. Thank you. Have a good day.
Thank you.